Now we all know the different types of chemical bond like ionic bond, covalent bond, coordinate bond, right, etc. So now let us start with covalent bond. So the covalent bond, actually the covalent bond will have the mutual share of electron with each other. Okay, this will take place in the polyatomic molecules also. So now let us consider the examples of hydrogen. Okay, so if we take hydrogen, we all know hydrogen means it has a diatomic shape. So diatomic means two hydrogen, that is two hydrogen atom attached with each other with a single bond. See here you see the first picture, hydrogen along with hydrogen, the both the side we are having one electron, so that combines to form one bond. Okay, again if we take oxygen molecule, the oxygen will have double bond. Okay, one oxygen along with this oxygen, it will have double bond. So which means their structure will be given by this. So the hydrogen will have single covalent bond, oxygen will have double covalent bond, and nitrogen, if we take nitrogen, it will have triple covalent bond. So triple bond. Nitrogen will have triple bond. So one nitrogen triple bonded with the another nitrogen atom. So this kind of structure is said to be the Lewis structure. Okay. So now we'll take the example of water molecule. Here the water is, this will be the skeletal structure. Here the hydrogen and another hydrogen will occupy at the terminal position, and oxygen is placed at the middle position. Okay, so now we have to calculate the valence electron. So first we have to write the skeletal structure, then we have to calculate the valence electron, and then we have to draw a single bond. At last we have to distribute the valence electron. Okay, so actually this refers to the lone pair. Okay, here the oxygen will have two lone pairs here, and at last we have to verify whether all the atoms satisfy the octet rule. So octet rule means the should occupy only 8 valence electron. Okay, so that refers to the octet rule. Okay, so now we'll take one more example, the Lewis structure for nitric acid. Here nitric acid means HNO3. So hydrogen, that nitrogen, it is surrounded by the three oxygen atoms. So now here you see 1 into 1 hydrogen plus 1 into, that is oxygen, uh, and nitrogen. So now nitrogen will be 1 nitrogen here into 5. So this refers to their valence electron, and comes oxygen. Here we all know the oxygen will have 6 valence electron, and here totally 3 oxygen atom are there, so 3 into 6. So this will be equal to 24. So totally the nitric acid will have 24 valence electron. Okay, so first we have to draw a single bond in this skeletal structure, and then we have to distribute this 24 electron. So now 24 minus 8. This will, so 8 refers to the octet. So now when we subtract the 8 lone pairs starting from most electronegative atom. So now here you see 24 minus 8 will be equal to 16. So now here you see the 6 lone pairs are distributed to 2 terminal oxygen. Here the oxygen will have the valence electron 6. So on the 6 electrons the terminal occupied. So remaining here 6 electron and here 6 electron. So totally 12 electron. And here you see 2 electron and here 2 electron. So totally 12 plus 4 will be equal to 16. So this way it will connected to hydrogen the so that it gets satisfied with the octet rule. Okay. So finally this bond, that is we have to verify it with the octet configuration. So now the nitrogen will have one lone pair short for the octet. Okay, so nitrogen should have 5 valence electron in their outermost shell. So which means here you see one, here one electron, here one, so 3 electron. The remaining 2 electron will occupy, that refers to the lone pair of the nitrogen. So that the nitrogen will have one lone pair shortage for the octet configuration. So move one of the lone pair from the terminal oxygen to form the another bond with the nitrogen atom, so that we are getting the structure as N double bond O for the nitric acid. Okay, so these are all the different leaving structure for the different molecules, that is sulfur trioxide, ammonia, methane, dinitrogen pentoxide. So these are all the different structures. Then comes formal charge. How to predict the formal charge? So first of all, we have to write the skeletal structure. Then we have to count the valence electron, and then we have to draw a single bond. Then we have to distribute the remaining electrons so that it should form the octet rule. Okay. So now here you see the carbon attached with the two oxygen. We all know oxygen will have 6 valence electron in their outermost shell, right? So which means the 6 electron, lone pair of electrons will get distributed as like this form. Then we have to verify whether all the atoms have octet configuration. Here you see 6 electrons. Then we have to satisfy the octet rule to the lone pair of the oxygen. So it will have two structures. That is, the carbon dioxide will have two structures because we can distribute this as like this structure 1 and also structure 2, which means here we can distribute this terminal electron and also we can distribute this terminal electron also, so that only we are getting the two structure for two leaving structure for carbon dioxide. Here you see 2 2 4 electron, and this 2 electron will form one bond, and again here 2 electron, and the one more 2 electron will form a bond like this. Also we can write the structure as this two pairs of electron as in the form of triple bond. Okay. So how to calculate the formal charge of an atom? So formal charge will be calculated by Nv minus Nl plus Nb by 2. Okay, so here the term Nb refers to the valence electron and Nl refers to the lone pair of electrons. Nb refers to the number of electrons that is present in the bond. Okay, that is refers to the Nb. Okay, so now we'll take the structure 1, Nv, that is the valence electron. So here the valence electron is 4 for carbon dioxide, and here you see the carbon dioxide will have 4 valence electron. Okay, so that is the carbon. For carbon, and lone pair, the carbon won't have any lone pair of electron, and the bonding electron, number of bonding electron is 8, that is divided by 2, so that we are getting the answer as 0. Okay, so when we calculate the formal charge for oxygen in carbon dioxide, so the carbon dioxide will have totally 6 valence electron. For that is for oxygen it has 6 valence electron, minus the lone pair, the oxygen will have 4 lone pair of electron, right? If we take the individual oxygen that is surrounded by 4 lone pair, and the bond pair is at only 4, so that is divided by 2, so which means you are getting 0. Again, for if we take for carbon, we have to follow the same procedure, so that we are getting the formal charge as singly bonded and also as triply bonded. Okay, see here you see the structure 1 and then structure 2, right? So once we have completed the formal charge calculation, then we have to write the structure as in the form. Then there will be an exception for this octet rule also. So there are totally 3 types. That is one with electron efficient central atom, and the molecules containing odd electrons. Then the last will be the expanded valence shell. Okay. So now we'll take the first case, BF3, boron trifluoride. Here the boron that is surrounded by 3 fluorine, their leaving structure will be given as like this. Okay. So here the fluorine will have 6 valence electron that is surrounded with the boron. Okay. So now if we move a lone pair of electron from one fluorine, here if we move one lone pair of electron to the boron, then their leaving structure will be given as like this form. Okay. Similarly, we can draw the structure for beryllium chloride, boron trifluoride also. Okay. Again, if a molecule contains odd electron, so that is for nitrogen dioxide and nitric oxide, all the atoms that will be arranged as like this form. Then the structure for PCl5 and then SF6. These are all the different examples that is given in your book. Here phosphorus that is attached with 5 chlorine. Okay, along with their valence electrons. Okay, again for sulfur hexafluoride. So now we'll move on to the second type, ionic bond or electrovalent bond. So here if we take potassium, so here the potassium will have the electronic configuration of argon along with 4s1. Again for chlorine, it will have the electronic configuration of neon. Okay, so now the ionic or electrovalent bond is nothing but this refers to the electronegativity. It refers to the electronegativity. So the electronegative is simply there will be an electrostatic force of attraction that takes place between the two atom or ion. So இப்போ நம்ம இதில் எக்ஸாம்பிள் NaCl எடுத்துக்கலாம். ஸோ சோடியம் குளோரைடில் கேட்டையான். ஸோ இதில் கேட்டையானிக் பார்ட் எது Na ப்ளஸ் Cl மைனஸ் எடுத்தோம்னா ஆனியானிக் பார்ட். அப்போ அந்த Na ப்ளஸ் Cl மைனஸ் அது ரெண்டுத்தையும் வந்து என்ன ஆகுது, நடுவில் ஒரு ஃபோர்ஸ் ஆஃப் அட்ராக்ஷன் இருக்குது. அதனால தான் சோடியமும் குளோரினும் வந்து என்ன ஆகுது, ஒன்றுத்தோட ஒன்று லிங்க் ஆகுது. அதனால தான் நம்ம நடுவில் நமக்கு ஒரு பாண்ட் வருது. ஸோ அந்த பாண்டை நம்ம என்னன்னு சொல்கிறோம், சிம்பிளி electrostatic attractive force. Okay, so that only makes the two atoms attached together, right? Similarly for potassium chloride also. Okay. So now comes coordinate covalent bond. Coordinate covalent bond. Simply we can tell covalent bond is the mutual sharing of electrons. So the one, the electrons that get shared by both the combining atoms, that is said to be the coordinate covalent bond. So that is when it gets the, that is when it donates the electron, then it is said to be the donor atom. When it accept means it is the acceptor. Okay. So now we'll take the example for ferrocyanide. So it is a complex compound, that is the coordinate compound. See here, Fe refers to ion, cyanide. The Cn refers to cyanide. So totally 6 hexacyano. So which means their structure will be given by Fe, that is surrounded by 6 cyanide groups. So now the structure of this will be given by BF3, and when we compare it with the ammonia NH3, the nitrogen will have one lone pair of electron and that is attached like this. So now comes bond pair. How to calculate the bond length, bond order. So here if we take the covalent molecule A and B, okay, so this refers to the radius, distance between the two molecule, two atoms, that is said to be the bond length. That refers to the X-ray study and also the spectroscopic study. Actually, their structure, bond length will be simply given by the distance between the two nuclei. Okay, that is the two covalently bonded atoms. That refers to the bond length. And now comes bond order. So here the bond length will be a single bond, double bond. There depends on the atom attached with each other. Then comes bond order. Here bond order is simply the number of bonds that is formed between the two bonded atoms in a molecule. That is said to be bond order. So first we'll take the example for hydrogen. Here you see hydrogen. Their structure will be given as H, single bond H, and the hydrogen will have the bond order 1. So now comes bond angle. So like that different examples are given. Here in bond angle, that refers to the angle of the bond. Okay, so here we can able to predict the shape of the molecule, and after that we can tell in which angle the bond is attached. Okay, if we take the methane CH4, they will have the bond angle of 109 degree 28, and here for ammonia will have 107 degree, and for water molecule 104. Okay, then next comes bond enthalpy. See this bond enthalpy, that refers to the minimum amount of energy which is required to break the 1 mole of a molecule in a particular state. Okay, so actually this bond enthalpy will be given by the unit kilojoule per mole. See now here you see delta H, delta H2. So these are all the enthalpy value, bond enthalpy value. See here the bond enthalpy for different molecule is given. Then comes resonance. Here you see resonance means we can able to write more than one structure for a compound or molecule. That is said to be the resonance. Here if we take the example of carbonate, CO3 2 minus is said to be the carbonate. Here the resonance structure will be given in these forms. See here the carbonate CO3 2 minus will have three resonance structure, because we all know how to calculate the valence electron. So first we have to check for the outermost shell. Okay. From that we have to predict the total valence electron, and then we have to distribute throughout the molecule. So which means we get the first structure, carbon surrounded by 3 oxygen with their valence electron. This is the first structure. Then the second structure is simply given by a double bond with the next oxygen atom, and the third structure will have the double bond at the another oxygen atom. So carbon that is surrounded by 3 oxygen atom which has a double bond, and that double bond will be occupied by any of the oxygen atom. Okay, but only one oxygen atom will occupy that double bond. Okay, so now this is said to be the resonance structure. Now comes polarity of bonds. So we all know the atom or ion will get attracted with each other by the bond, right? So that is simply we have related with the electronegativity. So now if we take the example hydrogen fluoride, here that will have a bond. Hydrogen and then fluoride will be attached with a bond. It is said to be a polar covalent bond because here the electron will be shared with each other. Hydrogen share one electron and fluorine will share another electron. So that refers to the covalent bond, right? So now comes dipole moment. So dipole moment is simply the polarity of the covalent bond. It refers to the polarity, right? So it will have the charge, right? And that will be represented by plus Q minus Q. We'll take the example plus Q and minus Q, which has the distance 2d, right? So now the dipole moment of a compound or a molecule will be given by 1 d by. They will be expressed by 1 d by. So 1 d by will be given by 3.336 into 10 to the power minus 30 coulomb meter. So this C refers to the term coulomb meter, right? So the different examples are given. See here you see the molecule HF, HCl, H2O, ammonia, chloroform,